In the previous two lectures, you have seen the concept of vibrations of one-dimensional monatomic linear lattice. And today we are going to see a similar problem of vibration of one-dimensional diatomic linear lattice. This is also a very important problem of lattice vibration. Like the previous two lectures, as we have seen, that we have divided the lecture on vibrations of one-dimensional linear monatomic lattice in two parts. In the first part of the lecture, we have derived a relation which is called dispersion relation, and in the second part we have seen the discussion of that relation. Just like that, here we will again divide our lecture on vibrations of one-dimensional diatomic lattice in two parts. And this is the first part of the lecture. And in this first part of the lecture, again, we will discuss the vibration of this diatomic linear lattice, and we will obtain the equation of motion, and solving that very equation of motion, again we will find a very important equation which is called dispersion relation. And then in the second part of this lecture, which will be provided further, we will actually discuss that result. Okay. So now let us see how we can write the equation of motion and how we can solve that equation of motion to get the frequency of the vibration of the lattice. And for this, you can see this figure. Actually, I have shown in this figure a diatomic linear lattice. When you say diatomic linear lattice, it means to every basis, two atoms will be attached. Okay, in this lattice, with a basis, two atoms will be attached. For a general result, I have assumed that the two atoms attached to a basis are not identical, but they differ in mass. So you can see actually here I have considered a one-dimensional linear primitive lattice with basis containing two atoms of mass small m and capital M. Actually, the even numbered atoms, let us say 2n, this has a mass small m, and the odd number atoms have a mass capital M. Okay, so these are the masses of the two atoms, and for calculation we assume that this small m is smaller than this capital M. This is our assumption. You may take a small m greater than capital M, but in this calculation we are going to assume a small m is smaller than capital M. Okay, so these are capital M, this is a small m, again this is capital M. It means we have assumed that the even numbered atoms, that is 2n atom, 2n plus 2, 2n plus 4, just like 2n minus 2, 2n minus 4, these have masses small m, and the odd number atoms, that is 2n plus 1, 2n plus 3, 2n minus 3, 2n minus 1, each have mass capital M. And these atoms are arranged on x-axis, as you can see in this figure. And as I have shown in this figure that the interatomic separation of this lattice is small a. It means the distance between two consecutive atoms, let us say this 2n minus 3 and 2n minus 2, these two atoms are separated by a. And in the similar manner, you can see that the distance between any two successive atoms is a. And so the repeated distance will be 2a. In other words, you can say that if we consider the distance between the two similar atoms, that is the distance between this capital M and this capital M, that will be equal to 2a. Okay. In fact, in the state of equilibrium, I have shown in this upper line, uh, the arrangement of atoms in this upper line is the state of equilibrium, and we have assumed that the atoms are located at the sites 2n minus 3, 2n minus 2, 2n minus 1, 2n, 2n plus 1, 2n plus 2, 2n plus 3, and so on. Okay, we have assumed it. Okay. Now let us consider this system is disturbed. How this system will be disturbed? As we have learnt in the problem of monatomic linear lattice, I have stated that if your aim is to disturb this system in equilibrium, you must pass some acoustic wave through it. So we consider that a plane progressive acoustic wave passes through this lattice, and due to the interaction of the wave with the atoms get disturbed, that get perturbed, and they start vibration about their equilibrium position. Okay, so this lower line here you can see is the disturbed state or the state of displacement of our system. Actually, you can see I have shown that at any time t, the 2nth atom, which was initially at this position, is now at here, where you can see, and its displacement is actually u2n. This displacement is u2n, as you can see it here. This is u2n. Similarly, I have assumed that the displacement of this 2n plus 1 atom, which is now displaced to this position, this is its original position and this is its displacement, and this displacement is actually equal to u2n plus 1. And in the similar manner, you can assume that the 2n plus 2th atom has been displaced by u2n plus 2. This 2n plus 3 atom has been displaced by this u2n plus 3. And in this way, you can also assume that the displacement of this 2n minus 1 atom, this is displaced by this u2n minus 1. Okay. So in this way, I have assumed that various displacement of the atoms from their equilibrium positions at any time t when they start vibration. Okay. Now our aim is to write the equation of motion. Actually, the detailed analysis of writing equation of motion I have discussed in the problem of monatomic linear lattice, the video of which was provided earlier. So if you want to understand the concept of vibration of this this one-dimensional diatomic lattice, you must watch the video on the vibration of monatomic linear lattice, because the idea which was developed in that case will be utilized here. So if you have not watched, you must watch it. Okay. You have seen in the case of monatomic linear lattice that we obtain the equation of motion, that is we can apply the Newton's second law of motion by applying Hooke's law. Okay. We find the force acting on an atom during vibration, that is the restoring force, in two ways. One, by applying Newton's second law of motion, and another applying the Hooke's law. So taking the Newton's second law of motion and Hooke's law under account, which we have learnt in the previous lecture, I have written here directly the equation of motion of the odd number atoms and the even number atoms. Actually, what I have explained just now, for your convenience, I have written here in language everything, because my aim is to provide a video which will help you in writing the answer in your university examination and different competitive examination like UPSC, BPSC, if you have taken physics as an optional subject. So you can see I have written all those things. So I am just again going to give a reading for it, but already I have explained it. So you can see, consider a one-dimensional linear primitive lattice with basis containing two atoms of masses small m and capital M, which are placed alternately along the x-axis with interatomic distance equal to a. This small m is the mass of each even numbered atom and capital M is the mass of the odd numbered atom. And for calculation, here I have assumed that this small m is less than this capital M. This is our assumption. And our system was initially in equilibrium. But when a plane acoustic wave is passed through the system, then the system gets perturbed and the atoms vibrate about their equilibrium positions. And as you have seen that this U2n minus 2, U2n, U2n plus 2 and so on, these are the displacements of the even numbered atoms. And similarly, this U2n minus 1, U2n plus 1, U2n plus 3, these are the displacement of the odd number atoms. Okay. Now, as I have told you that taking the Hooke's law and the Newton's second law of motion under account, now you can write the equation of motion of both the even numbered atoms and the odd number atoms. Okay. So the idea which was actually developed in case of monatomic linear lattice vibration, that has been utilized to write these equations of motion. Okay. If you consider that this F2n is the restoring force or the elastic force acting on the 2nth atom, which is responsible for its vibration, according to Newton's second law of motion, that will be equal to mass of the even numbered atom, which is a small m, times acceleration of the 2nth atom. And as U2n is the displacement of the U2 of the 2nth atom at any time t, so you know d2U2n by dt square, actually this will be the acceleration of the 2nth atom. So as according to Newton's second law of motion, force is the product of mass times acceleration. So F2n is written as m times d2U2n by dt square. But according to Hooke's law, this force is proportional to this relative displacement, that is U2n plus 1 plus U2n minus 1 minus 2un. How this factor comes, I have discussed in the case of my lecture on monatomic linear lattice. You can see the explanation there. Okay. And when you will remove the proportionality sign, you have to put a proportionality constant, and this mu is the proportionality constant, which is actually called force constant. So the restoring force responsible for the vibration of 2nth atom, that is F2n, is given as m times d2U2n by dt square equal to mu times U2n plus 1 minus U2n minus 1 minus 2un. Okay. And in the similar manner, if you assume that the restoring force or the elastic force acting on the 2n plus 1th atom is F2n plus 1, then that will be equal to mass of the 2n plus 1th atom, which is capital M, times its acceleration. And since its displacement is u2n plus 1, so acceleration will be what? This will be d2u2n plus 1 by dt square. So f2n plus 1 is m times d2u2n plus 1 by dt square. And again, according to Hooke's law, this force will be given by mu times what? This is u2n plus 2 plus u2n minus u2n plus 1. Actually, we have to consider the displacement of 2nth atom relative to the nearest two atoms. So, with respect to 2n plus 1th atom, its displacement will be u2n plus 1 minus un, and relative to 2n minus 1th atom, its displacement will be u2n minus u2n minus 1. Okay, and then taking the difference, you get that expression. Okay, so in this way, we have written the equation of motion of the 2nth atom and the 2n plus 1th atom using the Hooke's law, whose idea has been discussed in the lecture on monatomic linear lattice. Okay. Now, the solution of this equation we seek in the form of plane wave. And as I have told you that this system has been actually disturbed by passing the acoustic plane wave. So you can seek the traveling wave solution of this type. So u2n is given like this. This is a times e to the power I omega t minus 2kna. Okay. Actually here at the place of n we have to write 2n. Okay, and you know this is the just the plane wave. And similarly u2n plus 1, this will be given by b times e to the power I omega t minus 2n plus 1 into ka. You know this k is the wave vector of a particular mode of vibration. Okay. Here you must note that the vibrational frequency of both types of atoms is assumed to be same, and that is equal to omega. Why we assume that the vibrational frequency omega will be same for both atoms? Because you know, according to classical physics, the frequency of vibration of a system is same as that of the frequency of the source. Here we have assumed that our plane wave has a frequency omega. So this wave will impart a frequency omega into the both atoms. In other words, you can also say that the frequency of vibration for both atoms has been taken same because both types of atoms participate in the same wave motion, and that's why we consider that the frequency of vibration of both atoms will be same. But here you should also note that the amplitude of vibration of the even numbered atom, that is 2n, and the odd number atom, that is 2n plus 1, have been not taken same, but they are taken A and B, and A and B are different. Why we consider the amplitude different? Although it may be equal, but here we have considered it different because we have assumed that the mass of the 2nth atom is small m, and the 2n plus 1th atom is capital M, and for generality we consider that these two masses are unequal. Since masses of the two atoms are unequal, so in general you must consider that the amplitude of vibration of both atoms may be taken different, and that's why Their amplitudes have been taken different, but their frequency of vibration have been taken same, because both atoms participate in the same wave motion. Okay, I think you have clearly understand this argument. Okay, now after writing the plane wave solution of this equation 1, in which is actually u2n and u2n plus 1, in the similar manner you can also write the expression for u2n minus 1, u2n minus 2, u2n minus 3 and so on. Okay, but before that let us see, in our equation of motion there is d2u2n by dt square and d2u2n plus 1 by dt square. Now using this equation 2, you can find these accelerations by simply differentiating equation 2 two times with respect to t. So let us differentiate the first part of this equation 2, that is this u2n, two times with respect to time t, to get the acceleration of 2n plus 2nth atom. Okay, so you can see first of all we will find the first order derivative, that is du2n by dt. So this is d dt, and as you have seen that this u2n is equal to this much. This is what? This is actually a times e to the power I omega t minus 2 kNa. Now when you will differentiate it, you can see this will be I omega times a e to the power I omega t minus 2 kNa. Okay. Now again differentiate it. So after second differentiation we will write d2u2n by dt square, and that will be equal to what? Again I omega will be outside, so this will be I square omega square times a e to the power I omega t minus 2 kNa. But you know this I square is equal to minus 1, and this factor which I am crossing here, a e to the power I omega t minus 2 kNa, what is this? You can see this is actually u2n. So instead of that you can write u2n, and so we can write d2u2n by dt square is equal to minus omega square times u2n. Okay. Similarly, when you will differentiate this u2n plus 1 two times, you will get the similar result. The only difference will be what? The only difference will be there will be u2n plus 1 at the place of u2n. Okay, so I have written it here on the basis of this analogy, that d2u2n plus 1 by dt square, this will be equal to minus omega square times u2n plus 1. Okay, so in this way we have obtained the value of d2u2n by dt square and d2u2n plus 1 by dt square in equation 1. But our equation 1 also contains u2n plus 1 and u2n minus 1. Okay, and u2n plus 2 it also contains. So we will write here the expression for u2n minus 1 and u2n plus 2 on the basis of this equation 2. Only you have to replace this 2n by 2n minus 1 and 2n plus 2, and you will get those expressions. So you can see in the light of equation 2 we can write u2n minus 1, this will be b times e to the power I omega t minus 2n minus 1 ka, and u2n plus 2, 2n plus 2, and u2n plus 2, this is actually even numbered, and in case of even number you have to write actually for even number you have to write amplitude A, not B. So here actually there will be A, not B. Okay, and in the expression of 2n minus 1 there will be B, because this is odd. Okay, so here there will be A. Okay, and at the place of 2n there will be 2n plus 2. Now let us substitute all these values, that is the value of u2n minus 1, u2n plus 2, and these two values, these two accelerations in this, and also u2n and u2n plus 1. All these values will be substituted in equation 1. Okay, so let us substitute this. After substituting these, I have written here, you can see, using equations from 2 to 4, that is equation 2, 3 and 4, in equation 1 we get. You can see your equation 1 is what? This equation is actually equal to m times d2 u2n by dt square. But we have seen that this d2 u2n by dt square, this is equal to minus omega square u2n. So this will be minus m omega square u2n. But u2n, this is equal to what? This is a e to the power I omega t minus 2kn. Okay, and in RHS you can see there is mu times u2n plus 1 plus u2n minus 1 minus 2 u2n minus 2u, not n but 2n, right here 2n. This will be actually 2n. u2n. Okay, so I have substituted here all these values. You can see this is b times e to the power I omega t minus 2n plus 1 times k, and plus b e to the power I omega t minus 2n minus 1 into k. Okay, and here there is 2u2n and 2, and this a e to the power I omega t minus 2 k and a, this has been written at the place of u2n. Okay, now you can see this factor, exponential factor, e to the power I omega t minus 2 k n a. This is a common factor. Actually, in each term of LHS and RHS, this factor is constant, so that will cancel out. See, in first term of RHS, there is e to the power I omega t ka minus e to the power minus I 2n ka. Okay, and e to the power minus ik. Okay, similarly in the second term this factor is also present. In the last term this factor is already present. Okay, so this factor will cancel. I have not written it, but you can understand. So after the cancellation of this factor, what are the remaining terms? You can see these are minus m omega square a equal to. Now in the first two term of RHS, this b will be a common factor. So I have written here mu b times, and at the place of second term this e to the power ika remains, and at the place of first term e to the power minus ika remains. Okay, and at the place of last term only 2a remains here, and when you will multiply by this mu, this will be minus 2 mu a. Okay. Now you know that cos theta is equal to e to the power I theta plus e to the power minus I theta over 2. And that's why you can say that this 2 cos theta, this equals e to the power I theta plus e to the power minus I theta. So on the basis of this Euler's formula, can you say what will be this? This a e to the power ika plus e to the power minus ik. Here at the place of theta there is ka, so using this formula you can write that this will be equal to 2 cos ka. So you can write minus m omega square a is equal to 2 mu b cos ka and minus 2 mu a. Now let us arrange the terms. When you will bring the terms in RHS in LHS, what will happen? You can see this minus 2 mu a will become plus, and this plus 2 mu b cos ka will become minus. So our equation will now written as 2 mu minus omega square m times a minus 2 mu cos ka times b is equal to 0. Okay. So actually simplifying this first equation, that is the first equation of equation 1, we have obtained that result. And you can see the second equation of this equation 1 is also similar. So when you will simplify that equation in the same manner, then what you will get, you can see. Actually, when we will simplify that, instead of this small m, there will be capital M, and a and b will be interchanged. At the place of a, there will be b, and at the place of b, there will be a. So you can see I have written it on that basis directly here. So similarly, we can write minus 2 mu a cos ka times a plus 2 mu minus omega square capital M times b equal to 0. Okay. Now you can see that equation 5a, this equation 5a and this equation 5b, actually these two equations are a set of homogeneous linear equations. And according to the theory of determinant, these equations will have non-zero or non-vanishing solutions for a and b only when the determinant of the coefficient of a and b will vanish, will be 0. This is in accordance with the theory of determinant. Okay. So on this basis you can take that the determinant of the coefficients of a and b in equation 5a and 5b must be equal to 0. So let us see. The coefficient of a in equation 5a is what? This is 2 mu minus omega square small m. And that of b is minus 2 mu b cos ka. So I have written here that determinant of 2 mu minus omega square m and minus 2 mu cos k. Now see equation 5b. The coefficient of a here is minus 2 mu cos k. So I have written it here, you can see this is minus 2 mu cos k. And the coefficient of b is 2 mu minus omega square m. Okay. And this determinant will be equal to 0. Now solving this determinant, we can obtain the value of omega. Okay. And the solution is very easy. You can see this will be what? This will be 2 mu minus omega square m times 2 mu minus omega square m minus 2 mu cos k times minus 2 mu cos k, which will be 4 mu square cos square Ka, and that will be equal to 0. Now let us multiply the first two factors in LHS. So this will be 2 mu times 2 mu. This will be 4 mu square. Again 2 mu times minus omega square capital M. So this is minus 2 mu omega square capital M. Okay. Now minus omega square M times 2 mu. This will be minus 2 mu omega square small m. And finally minus omega square small m times minus omega square capital M. That will be omega 4 m times m. Okay. And the last term is at is you can see, and this will be equal to 0. Okay. Now the first term, see it here, and the last term both contains mu square factor. Okay. Both contains mu square factor. So these two terms will be combined. Okay. And I have also taken this product m times m as a common factor. Okay. Then you can see here there is omega 4 times mm. When you will take this mm as common factor, here will be omega 4. Now in the second and third term, you can see this 2 mu times omega square is common, and the remaining terms will be then what? M plus m. But in this term there is this m times m is not present, so you have to divide it. Okay. And finally the combination of the first term and the last term you will get plus 4 mu square times 1 minus cos square k. And again, as it does not contain m times m, so you have to divide it by this. Okay. And this is equal to 0. Now you know neither capital M nor small m is 0. So this product is not equal to 0. Okay. And as the result is 0, so if m times m is non-zero, definitely the factor inside this square bracket must be equal to 0. Okay, must be 0. And you know this 1 minus cos square Ka is equal to what? This is sin square Ka. Okay. So our result is omega 4 minus 2 mu times m plus m over m times omega square plus 4 mu square sin square Ka by m times m, and that is equal to 0. Okay. Now you can see this is a quadratic equation in omega square, not in omega, because here there is omega 4, here is omega square. So this is in the form of ax square plus bx plus c is equal to 0. You can see at the place of x square there is omega 4. So you can say here x will be equal to omega square. And at the place of b there is minus 2 mu m plus m by m times m. Okay. And at the place of c there is 4 mu square sin square Ka by mm. Now applying the formula for the roots of the quadratic equation, which is x equal to minus b plus minus root over b square minus 4ac over 2. We can find the value of omega square, not omega, mark it, because it is quadratic in omega square, not in omega. So what will be omega square? Utilizing this formula of quadratic equation, you can see minus b, but b is minus 2 mu m plus m by mm. Okay. So minus minus will become plus, so this is 2 mu. And here I have actually simplified it, m plus m by mm. When you will divide the two terms separately by the denominator, what will be this? This will be capital M by mm, so this is a small 1 by m plus. Now a small m by mm, a small m will cancel out. This is 1 by capital M. So instead of m plus m by m into m, I have written here 1 by m plus 1 by capital M. Okay, and plus minus. Now see, b square. B square means 4 mu square m plus m by m times m whole square. But you have seen that m plus m by m into m, this is 1 over m plus 1 over capital M. So b square will be equal to 4 mu square times 1 by m plus 1 by capital M whole square, and minus 4ac. A you can see is 1 and c is this much. So 4ac, that will be simply 4c because a is 1. And when you will multiply it by 4, this will be 16 mu square sine square ka and divided by mm. Okay, and whole divided by 2a, not 2 but 2a, but a is 1, so here there will be only 2. Okay, only 2. Now you can see in both terms inside this square root, this 4 mu square is a common factor. So when you will take 4 mu square as a common factor in the terms inside the square root, and when you will write it in outside of the square root, that will be 2 mu, because 2 mu will be the square root of 4 mu square. Okay, 2 mu. And the remaining terms will be what? This will be 1 over m plus 1 over m whole square minus, here 4 mu square has been taken as a common factor, so only 4 remains here. So 4 sine square ka. But the 2 factor 2 in all the terms in the numerator and the denominator will cancel out. So after cancellation of 2, you will get omega square equal to mu times 1 over m plus 1 over capital M plus mu times a square root of 1 over small m plus 1 over capital M whole square minus 4 sine square ka divided by m times m. This is the expression for the frequency of vibration, a square of the frequency of vibration. How this frequency of vibration will vary in accordance with the wave vector k, this relation shows. And you know, a relation which relates the frequency with k, that is wavelength, that is called dispersion relation. So this is the dispersion relation in case of the linear diatomic lattice. Okay, you know, when we have considered the case of the vibration of monatomic linear lattice, then you have seen that if we consider only the positive value of omega, then we find that in the case of monatomic linear lattice, there is only one value of omega for each single value of k. But here you can see that in case of diatomic lattice, omega has not only one value, but it will have two values. And those two values can be obtained by taking this plus sign and this minus sign. So when you will take plus sign, you will get one of the values of omega square, and when you will take minus sign, you will get another value of omega square. So there are actually two values of omega in the case of diatomic linear lattice vibration. Although in case of monatomic linear lattice vibration, you have seen there was only one value of omega for a particular value of k. Okay, actually I have denoted these two values of omega by omega plus and omega minus. Here the subscript plus in subscript plus indicates that you have to consider the plus sign of equation A1. And when you write omega minus, that will be obtained by taking the negative sign. So you can write omega plus square will be what? For this you have to you should take this plus sign. Okay, and so our result is omega plus square equal to mu times 1 over m plus 1 over capital M plus mu times a square root of 1 over m plus 1 over capital M whole square minus 4 sine square Ka over mm. Okay, and when you will take this minus sign of equation A1, then you will get the value of omega minus square, and that will be simply equal to mu times 1 over small m plus 1 over capital M minus mu times a square root of 1 over small m plus 1 over capital M whole square minus 4 sine square Ka divided by m times m. So actually there are two branches of frequency, two branches. Actually we will see in the second part of our lecture that the frequency denoted by this symbol omega plus, this is the frequency of optical branch. This is called frequency of optical branch. Okay, and this omega minus, this is called the frequency of acoustical branch. But these all things we will discuss in the second part of the lecture, which you will get very soon. Okay, so after watching this video, you must watch also the second part of the lecture, because in this lecture I have only derived this dispersion relation. There is not a very large physics here. The physics behind, what is the physics behind this result, that will be discussed in the second part of the lecture. So the second part of the lecture will be the discussion on this, and that will actually explain what is the physics behind this. Okay, so that will be a most important lecture, and I hope you will must watch that video. Okay, thank you very much.